Hello, Kyle here. I've got two problems to look at in this video in response to some homework questions that were sent to me from MyLabs Plus. So both of these problems are from the first section of Unit 1, functions, and in both cases they're asking us for the domain, this one's asking for the range. So let's do a real quick just review of functions. So remember, a function is a relationship between two sets. We've got one set over here. It's going to work. Oh, it's a circle, huh? Let's go back. Make that a square. One set here, one set here. And these two sets are related via an input-output relationship. Right? You plug something into the function, that's the input, you get something out. That's the output. That's the idea. So the value that's being plugged in algebra, classically, this can be thought of as the x value, whereas the output a lot of times is thought of as the y, or we write that as f of x in function notation. The set of inputs is called the domain, and the set of outputs is called the range. So for instance, I might have a function, maybe I'm trying to describe the distance of an object. We'll call it d, and that distance is being determined as a function of time, right? How much time is going by? The object's maybe moving at 20 miles per hour. So if I were to know the number of hours, let's say 3 hours, right? Well, then the distance the object has traveled, 20 times 3, gives us 60. Now, the time value in this case is representing the input, the independent variable. Independent variable, excuse my terrible handwriting. Whereas the output, this 60, how far I've traveled, well, that's the member of the range. And that 60, in this case, let's say it's 60 miles, was determined by the time value. So we call this 60, this output, the dependent variable. Dependent variable. So a function, again, is just describing this relationship, this input-output relationship. And when we talk about the domain, we're referring to the set of values that can be plugged into this function and have an associated value in the range, right? You plug something in, you get something meaningful out. The range is concerned with all of the values that I feasibly could get as an output in this function. So let's take a look at these problems here. It says use the graph to determine the domain and range of the function. Well, we don't have a rule, we just simply have a graph. So first thing to consider real quick is there's open circles here, and these open circles are trying to depict that at that specific point that is not being included, right? Whereas if I had a solid dot, let's say this was solid over here, well, then it would say, okay, this value, if you notice, has an x value of 2 and a y value of 4. Well, that 0.24 is actually included in the set for this function if it was a solid dot. Now, in this case, it's open, so those endpoints are not being included. So when we think about the domain of this function, we're looking at the independent variable, the input, which is the horizontal axis, the x. Okay. You always want to associate the domain with x values if we're going to consider just the xy plane. Right? I mean, this x could be a t, it could change, the variable itself could be a different letter, but in terms of x and y, x is the domain and then y is the range. So when it says what is the domain for this function, it wants to know, well, what's the set of all x values that exist for this function? You plug them in and they have a corresponding y value. So we're going to read this left to right, right? The smallest x value in this case is 1, 2, 3, 4, 5, 6, and that is a -6. So we know we can go as far as -6 to the left, and then as we move right, we can go as far as 2 to the right. Now, with interval notation, remember, if this was a solid circle, we would want to indicate that point's included, we would use a bracket. Use brackets to represent the solid circles or values that are included. But in this case, because it's an open circle, we're going to use the parenthesis. The parenthesis means you can go up as close as you can imagine the 2, but 2 itself is not actually included. Same thing with -6. So in this case, it's a multiple choice question, so I'm just going to circle it. D is the answer. And now the range the y values that exist for this function. Well, y runs on the vertical axis. So if you notice, the smallest y value is -2 right here, and the largest y value is 4. So we can be as small as -2, not including -2, and as large as 4. Again, that's supposed to be an open circle. As large as 4, not including 4 itself. So the range is -2 to 4. All right, so let's take a look at the next problem, the one with the rule. So you could feasibly graph this and take a look at the graph, but with this class for now, we're only concerned with really two things, and then later on in Unit 4, we'll introduce a different type of function. But when it comes to specifying the domain given a rule like this, the question is really just asking, are there any x values that can't be plugged into this function? I'll give you an example. 1 over x, right? If this was my function, if f of x is 1 over x, then x could not be a particular number, right? X couldn't be 0. If x was 0, the value I would try to get corresponding within the range would be something uncountable, right? 1 divided by 0 is not a countable value. It's not a real number. So for that reason, x equals 0, the x value of 0 is not in the domain of this function. So we would actually, well, I'll write it out real quick. Right? In this case of the one I illustrated, f of x, the domain would be everything but 0. To the left of 0 and to the right of 0, but not 0 itself. Okay. When it comes to specifying domain, you've only got to worry about two things at this point. You got to worry about denominators. Right? So I just showed you where you got a denominator. Right? If you have a denominator, it's full erase. Look for two things. Right. 1, expressions in the denominator. Expressions in the denominator. As an example, maybe I've got a function and its role is equal to 2 over x minus 5. Well, I've got an expression in the denominator, right? There is a division operation going on in this function, and we know we can't divide by 0. So anytime you see a expression of x or t, whatever the independent variable is, if you see expression of that variable in the denominator's place, you want to set that denominator to 0 and see if there's any value that's going to make it equal to 0, because if there is, that value can't be part of the domain, right? We can't divide by 0. So in this case, we know x minus 5, whatever it is, can't be 0, right? Because we can't divide 2 by 0. So if you solve for this, we find out that x cannot be 5. So then, of course, again, you write this out. Well, x can be anything to the left of 5, or that is the union symbol means or it can be anything larger than 5, but it can't be 5 itself. So that's one thing to look out for, expressions in the denominator. The other thing to look out for is, I'm going to write this, let's see, radicals with an even index. And that's just a fancy way of saying something that is simple. So let me explain. A radical is a root operation. So square root, for instance, is a radical. You can take the cube root, you can take the 4th root, 5th root, so forth. So the index is just that value here, that n. This is the index. It's the root that I'm taking. We're mostly going to see square roots, but you can really see radicals of any index, and we'll see more and more of those as the class goes on. But the idea is, if you're taking a even root of something, let's say the square root of something. I want to take the square root of that x minus 5 again. We'll call this function g of x. Well, whatever that x minus 5 is, what has to be true about it? Well, if we're taking the square root, we know it has to be something that's not negative, right? Well, the square root of something like -9, or the square root of -10, right? We know the square root means we want to figure out the value when squared gives us, in this case, this -9 or this -10? Well, we know there's no number times itself that's going to give you a negative value, right? Negative times a negative is a positive, and a positive times a positive is a positive. So there's no way to take the square root or any even root of a negative value. So in this case, g of x, we've got the square root of x minus 5. Because we're taking the square root of this x minus 5, we know it can't be negative. So I set it greater than or equal to 0. And then if you solve here, just add the 5 to the other side. You know, okay, well, if x minus 5 is going to be non-negative, then x itself has to be greater than or equal to 5. So we would say the domain for this set is any value of x that is 5 or larger. Notice I put the bracket around 5 because in this case we're including 5, right? You can take the square root of 0. 0 times 0 is 0. So those are the only two things to look out for when it comes to specifying the domain algebraically, at least for the time being. Two things. Is there any denominators? Is there any roots, even powered roots? Second root, fourth root, so forth. So in this case, it's just a linear function. There's no, we're not dividing by anything. We're not taking the square root of anything. So for that reason, we can plug in any number, any real number in the world here, and we'll get a value. You can multiply any real number by 2 and subtract 4, and that number will be another real number. Right? We're not worried about dividing by 0, taking the square root of negatives. It's just a simple linear function. So if you don't see either of these two things, all you got to do right away is say, okay, well then the domain is everything, all real numbers, we say. It can be as small as negative infinity. It can be as large as positive infinity. Any value can be plugged into this function here. All right, hopefully that helps. And if you have any further questions about the video or anything else, feel free to let me know. Take care. Thank you. Bye.